You can all hear me, right?
Yes, sir.
Great. So, like I told you in the uh, previous class, I'll be teaching you second and fourth module. A small problem here is that uh, there are a few ideas which you learn in first module that should be used in second module. So I think the right thing for me to do is that I will start from the basics. So just to be clear, yeah. So what in first module, what have you discussed so far? Can someone tell me? In first module, what happened so far? Anyone? Yeah, why didn't I get an answer? one of my file is actually missing. That's why I'm taking some time. Where is it? Can you see the screen right now?
Yes, sir. Yes, sir.
Okay. Sorry for the delay. Uh, one of my file was actually missing. I had to download it. So I don't think we did not discuss anything in the last class. I probably asked you what is stress or something. That's it. And also, you did not answer my question regarding what you have discussed in the first module so far. So I will start from the basics. So since this is an online class, it's very difficult to actually know if you have any questions at all. You need to immediately ask me if you have any questions. So what is stress? Let's say you have when I asked what is stress, someone told, I think it is the resistance to external forces. That's actually right. And I also told you that it's not the force, it's the force per unit area, and it is a vector. I'm sorry, it's not a scalar. Let's see if it's a vector or something else. Since it's the resistance to force, it's highly likely that it will have multiple directions, right? If you have force in x direction, if you have a force on an object in x direction, you will have certain type of stress. If you have stress on force on y direction, you will be having different type of stress, right? So it's highly likely that it will have multiple directions, and let's see if that is the case. So we would like to define stress. That's my first job here. Use black. Let's say you have an object of random shape, completely random shape, and you have different forces on the object. This is a distributed force, okay. What do I call it? Let's call it P. F4 5 all types of forces, and let's say the object is in equilibrium. So what does that mean? If something is in equilibrium, what does that mean? Can someone tell me? Remember any lesson from engineering mechanics? What do we mean when we say that an object is in equilibrium?
Sir, the resultant will be 0.
Right, net force on the object will be 0. So here, because of all these forces, it's not accelerating or anything. It's staying somewhere, and net force on the object is 0. So when that is the case, we'll be able to use equilibrium equations. Net force if net force is 0, force being a vector, you can use it in every direction. Net force in x direction is 0, net force in y direction is 0, net force in z direction is 0. So that is the case with the whole object, and you can divide the object into different parts, and each of the part will be in equilibrium. So I'm going to simply cut the object. Okay, I'm going to make a cut. Okay, where do I make the cut? Okay, I'm making the cut here, right? So this is the don't know if this makes sense. This is the cut part and this is the cut surface. And the same forces, F1, F2. And now this should also be in equilibrium. If the whole object is in equilibrium, I can cut it and each of the parts should be in equilibrium. But one issue is that I need to show the internal forces of the first object with respect to the cut part here. So what are those internal forces? So those internal forces are the reason why we have the idea of stress. Had it been a simple case, if it's a bar, let's say it's just a bar with moment and force on either side. If you cut it here, it's very easy for you to draw the equilibrium of each part. You already know how to do that. Just draw the force and corresponding torque here. But here the issue is that this is a continuous object, and it has mass, it has volume, and it has forces per area throughout the cut surface. How do we represent those forces? That's the issue here. So what we do is that we'll divide into very, very small areas the cut surface, and consider a small area called delta A, a differential area called delta A, and I need to represent all the forces on the cut surface, right, to make sure that it is in equilibrium. And I have chosen a small area delta A, and what could be the force on it? Force, some force we don't know, force with magnitude F in that's a vector, so there will be 3 directions. So let's so we have to call it delta Fx delta Fy and delta Fz. So the force on the differential element will be a vector, so hence I split it into 3 components, rectangular components, delta Fx, delta Fz, delta Fy. So these forces are acting on the small differential element delta A. So there are many such differential element on the cut surface. So we need to define all these forces in all these areas to draw the equilibrium or to define the stress. So I'm using the term stress here, stress everywhere in the cut surface. Since there are three components here, we have to define stress in such a way that there will be a component called tau xx limit delta A tends to 0 delta fx by delta A. Similarly, there will be a component called tau xy limit delta A tends to 0 okay, some people are trying to join. Okay. Similarly, third component called tau xz. So you can see what is happening here. The cut surface I've made is perpendicular to x direction. You must note that the cut surface, cut area is perpendicular to x direction. So the first letter in the subscript of tau represent that direction. So x is common here, tau x, tau xy, tau xz. See, I'm taking so much time here to explain the concept of stress because this is very important and fundamental for the subject of strength of material. So for all the other subjects like advanced strength of materials and finite element methods, there are so many subjects in mechanical engineering which will need this idea of stress. So make sure that you understand it correctly. So the first subscript represent the direction perpendicular to the area here, and the second subscript represent the direction of force on the elemental area. So tau xx is delta fx by delta A, delta A being a differential element tends to 0. Similarly for these two components.
Hello sir.
Yes.
Sir, আমার খুব নেটওয়ার্ক প্রবলেম স্যার, সাবজেক্টটা কি স্যার?
Can you speak in English?
Sir, may I wants to know which subject?
Which subject am I teaching?
Yes sir.
Strength of material.
Thank you sir. Sir, I have a network problem, so I don't know which subject.
Okay, that's a question I did not expect. Anyway, we've already had a class. This is the second class. I think I did not take anything in the first class, but we did discuss a few things. So I did not expect you'd need an introduction. Anyway, I think many people must already know this. So let's continue. So we were wondering what kind of quantity this is. So this is definitely not a scalar, right? Because we already have three components. So this is definitely not a scalar. And is it a vector? It seems it's a vector because we already have three components. Usually vectors have three components. Force has three components: fx, fy, and fz. So far we only have three components. So is it a vector? Actually it's not. So what you need to understand here is that stress is defined at every point. Let's say we have for this case we have chosen this point, right? This point here. I've cut the object here and I've chosen a differential element area on this point. Let's call it, I don't know what we call it, point Q. Okay, this is point Q. And in this case I cut in a direction perpendicular to x-axis. So if you actually see here, I can also cut the object in the direction perpendicular to z-axis also. Okay, this is the cut area. Same thing can happen. Here also you can have three components of force, and now you can also cut in the area perpendicular to y direction. So there will be a third picture. So the third picture will look it will look something like this, the exact thing, and it is cut in the third direction. So again delta A. Okay, three forces. What are the forces? Delta Fx, delta Fz, delta Fy. So here just like the way I first cut the object in a direction perpendicular to x-axis, I can also cut the object in a direction perpendicular to z-axis. It will look something like this, and I can define three components like that, right? So for this is case 1. These are three cases. Just like the first case, for the second case also I can define these components. Tau. Now first subscript, what does it represent? You tell me. I told you that there are two subscript. First subscript represents something, second subscript represents something. Can someone tell me? I've just told you. What does the first subscript represent? Anyone? It represents the what? represents the area of cut, right? The direction. So the first cut was perpendicular to x-axis, hence x everywhere. The second case, that is perpendicular to z-axis, so z everywhere. I can define tau zx, tau zy, and tau zz, just the way I have defined here. Similar equation. This will be tau zx will be limit delta a tends to 0, delta f x by delta a. Similarly, for the third case, I can define tau yx, tau yy, and tau yz. So how many components so far? So we are trying to define stress. It seems that there are so many components for the quantity. So how many so far? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 components so far. So you need to represent, you need only one number, one magnitude to represent a scalar, and you need 3 real numbers to represent a vector. And here it seems that you need 9 components. So it's neither a scalar nor a vector. It is something more complicated. It's called a tensor. Okay, a tensor. So how do we write this? Tau xx, tau xy, tau xz. Tau yx, tau yy, and tau yz. Tau zx, tau zy, and tau zz. Let's put this inside a matrix. So all the components we have defined so far, all the 9 components we have defined so far is here in the matrix, and this is called a tensor. So stress is neither a scalar nor a vector, it's a tensor. So actually these terms called vector and tensor are used in different contexts. So tensor, the scalar is known as the tensor of 0th order. Vector is known as the tensor of 1st order, and this can be said to have 2nd order. So that's the okay. Anyway, that you don't need to worry about that. So what you need to understand here is that you need 9 components to define stress, and it is called the quantity is called a stress tensor, and you can represent it this way. Okay. Okay, this scheme is a different fine, it's okay. All right. So here is the so earlier I showed you that we need 9 components to properly define stress, and we have cut an object in 3 different ways. So here what we have done is that this is a differential element within a 3D object. Just like the differential area, a differential volume with dimensions dx, dz and dy. So just the way we cut in the previous case, we have cut out a very small differential element, and each of these has an area. So what is the area? Well, that's difficult here. dz depends on the side. So this side has area dy dx. This side has dy dz, and for this one that is dx dz, etc. Now all those components I have defined is also shown here. This is the first cut, this side. Okay, this one was the cut perpendicular to x-axis, and the component perpendicular to, so the first subscript represent the cut area. So for these 3 components, the first subscript is common, tau x. It's common because that represents the same area. And tau xx means, so the second subscript represent direction, x direction, y direction, z direction. 3 components. The same 3 components we defined earlier. Here it is shown using a differential volumetric element. That is the only difference. So since the object is in equilibrium, you will have same components on the other side. So this cut surface, this is perpendicular to y-axis. I think I've used Z in the previous picture, but forget about it. Does not matter. It can be Z or Y. Anyway, note that I've used Z in the previous picture. So if this is y, that will be perpendicular. The area is perpendicular to y. Hence, y is common in all 3 components as first subscript. Second subscript represent direction. So tau yy, tau yx, and tau yz. Similarly, in the z direction, you have an area, and first subscript represent the area. Hence, z is common everywhere. Tau z, tau zy, so zx. Second one represent direction. You can again see that. So for all these components, there will be an opposite phase, and same components can be written over there also. So this is stress. What we have been doing so far. We have been trying to define stress. It seems that it is a very complicated quantity, but we can use the idea called tensor to define these. So the stress components which are perpendicular to the area on which it acts are known as normal stresses, and those components which act parallel to the area are called shear stresses. Hence, tau xx will also be written as sometimes sigma x. Sigma x means normal stress in x direction on the plane perpendicular to x axis. Tau xx, okay. Similarly, tau yy may also be written as sigma y, and tau zz may also be written as sigma z. That is something else to remember. Okay, that 11, I think you have class now. Well, you have class from 12 only, right? So anyway, we will not deal with 3D in this course. We are unlikely to deal with this 3D stress component for most problems. We will usually be dealing with 2D case. So how will that look like? Here I have replaced normal components with sigma x, sigma y, and sigma z. So this is a 3D case, and for 2D case we will not have that third component, z component. So we will usually be dealing with just we will usually be dealing with just this. The third component is completely gone. So the third area is gone, third direction is also gone. So one row and column missing. Sigma x, sigma y, tau xy, tau xy and tau yx, not z. xy and yx. Now one more simplification that we are going to make here is that let's consider the differential element delta A, and let's say this is x direction, sigma x sigma y, and this is tau xy because this is acting on the surface, same surface perpendicular to x-axis, and hence first subscript x, and the stress is in y direction, hence second subscript y. And this is tau yx. Similarly, here also you have tau yx, y x, and tau xy. Okay, I hope you understand. Xy. So here if you take a moment about this point here, you will actually see that this sigma y is has the same magnitude and it's in opposite direction, and here sigma x also same magnitude opposite direction, but these two are tau yx and tau xy are causing twisting action in different direction. And just like the stress normal stress components on the opposite direction, they also must be the same in magnitude. Do you understand that? If I take moment about this point, these two will be causing moment in a different direction and they must have the same magnitude, hence tau yx should be equal to tau xy. Tau xy should be equal to tau yx. Why am I writing Z every time? Tau yx. This is another important concept in stress, and these are called complementary shear stresses. Tau xy and tau yx are called complementary shear stresses because they complement each other, just like sigma y and sigma y in other two directions. Tau xy and tau yx complements each other and they are equal in magnitude, hence the same tensor can also be written like this, because tau xy and yx are the same. Xy and yx are the same, no difference. So just like xy and yx are same, tau xz and zx are same, tau yz and tau zy are same. So what does that say about the matrix? If these components are same, the matrix is said to be symmetric. The transpose of the matrix is equal to the matrix itself. That is a very important property of the stress tensor. It is symmetric. Hence, how many independent components are here? First we thought there were 9 components for the stress tensor, but it turns out that many shear stress components are equal to some other components. And hence the total number of independent component in stress tensor is not 9, it's actually 6. 1, 2, 3, 4, 5, 6. Because these 3 are equal to each other. So there are no, we don't have 9, we have 9 components, but only 6 independent components. Some of them are equal to each other. Okay, I'll stop for today. So I'm not really sure if you have understood all this. If you haven't, you must have asked. You can still ask. Next class also you can ask. So any questions right now? Any questions? Any questions?